forward. All right, so this section is going to be on solar activity. We're going to start with a little video. So these are all actual videos from the surface of the sun. You see how it's all like loopy-loopy? Those are following the lines of magnetism. Okay, so there were examples of all of the different types of solar activity in that video. So I'm just going to rewind and go through a few of them. First thing, solar activity is all due to these structures called sunspots. And I'll explain what causes a sunspot and why that leads to more activity. But first thing I want you to really focus on is the fact that, like last week, I was talking about how the sun has between 1 and 10 million poles, magnetic poles. Just like on Earth, we have the north and south, we have 2 poles, but on the sun, between 1 and 10 million. So you can see, even just here, my laser, how it, all of the activity follows these kind of loopy lines. And so these loops show you exactly where, excuse me, where 2 of the poles would be. So it just follows the lines of magnetism. Just like on Earth, which I mentioned last week, Earth has 2 poles, and it's definitely more rounder than that. More rounder, geez, my English is like suffering. And you've got lines of magnetism that come out like that, and then they kind of get dragged behind like that. So you see how it's like from one pole to the other pole makes these loops. So that's what you're seeing here, okay? So first thing is, from the least violent to the most violent, these are called prominences. And again, I'll go through each one again, but I just want to show you examples. So prominence is basically like an arch of gas that's coming out from the surface. A lot of them are much bigger than Earth. This is something called a solar flare. Okay, so when you have, I'll just turn the volume down. When you have gas that's basically kind of being flung upward, but most of it falls back down, more prominences, there's another flare there. So flares increase the strength of solar wind. Just pointing out here that sunspots move around on the surface and they also rotate. You can see it rotating that way. And here you've got, there's another solar flare. You got flares here. But sometimes you see, I'm trying to remember where I saw it, where you see really big bursts of gas that get kind of like flung out from the surface. I know they had at least one of them in here. you can see a lot of activity around the sunspots. Maybe it's here. If it gets flung outwards, no, this is also just a flare because most of it's falling back down. Maybe it was happening towards the end. That's just an X-ray of sunspots. Here, I think this is it. So you'll see that it basically gets, it gets flung out of the surface. That's something called a coronal mass ejection. Here's another one on the right-hand side. So the difference between a solar flare and a coronal mass ejection is the size and the fact that a coronal mass ejection is just huge amounts of gas being flung out. But like I said, I'll go through each one individually. So the gases of the inner zone and the atmosphere are in constant motion. That's why the surface of the sun appears kind of grainy and not smooth. So because of convection, in the convective zone, you've got this rising and falling of gases. Gases are also moving because the sun rotates on its axis. So you can see its rotation here. This is in a peak activity cycle. You can see how much activity there is here and here. But the difference is that the sun isn't actually rotating at the same speed at the poles versus the middle. Because if you compare it to the rotation of Earth, Earth is solid on the outside. And so the whole outside of the Earth spins at the same speed. But the sun doesn't do that because it's a gas. Closer to the sun's equator, it only takes 25.3 Earth days to make one rotation. But at the poles, it takes almost 33 days. So the poles rotate much slower than the equator does. And that's going to have a huge effect on the magnetic fields. The average for overall the sun is one rotation every 27 Earth days. So the combination of this up and down movement of gases in the convective zone and the movement of the sun's rotation produces magnetic fields. Now, magnetic fields are going to slow convection down. This is the key. The stronger the magnetic field is, the more it slows down convection. If you slow down convection, because remember, convection is bringing hot air up and then cool air sinks. So if that process is slowing, that means that there's less heat being brought up from deeper within the sun. Okay, less gas transferring heat. So there's regions of the photosphere that are near strong magnetic fields. They're up to 3,000 degrees cooler than the areas around them. And these are called sunspots. When you're looking at videos or pictures of the sun, they're going to appear black. But in reality, if you were to actually take them off the surface and put them just kind of hanging in space, they would be brighter than the full moon. So just for comparison, we've got the size of Earth is this blue dot right here. And so you can see how big sunspots, like that sunspot right here is as big as Earth, right? Same thing over here. And again, because the equator moves faster, it spins faster, you're going to see more sunspots towards the equator because that's where the magnetism is the strongest. Excuse me. Okay. Oops, I got a little bit covered up. Large sunspots can be more than 100,000 kilometers in diameter, which are several times the size of, pretty sure that says Earth back there. So this is just a closer up view of a sunspot. Again, remember the color of stars is due to the heat, but even though like you might think, okay, well, black means that there's no heat at all. Not true, but you see how this is yellow and right around the edge of the sunspot, it becomes orange. Orange is cooler than yellow. And it only appears black just because of the sheer brightness of the area around it. Now, astronomers found that sunspots first appear in groups halfway between the sun's equator and their poles. As they disappear, new ones seem to appear near the sun's equator. And that shifting in the sunspots was one of the first indications that the sun rotates. You saw in that video how they basically just shined the sunlight on a white surface, and you could actually see the darker areas of the sunspots, and you could see them moving through a lens, of course. And the number of sunspots changes according to an average 11-year cycle called the sunspot cycle. So every 11 years. And I forgot to check where we are in the sunspot cycle at the moment. Sunspot cycle 2022. Ooh. I just typed in sunspot cycle 2022 and I got from the NASA website, we're in solar cycle 25, and there was a mid-level solar flare on January 20th. So it was just a couple weeks ago. I think we're at a peak right now. Anyway, I'll have that load up and we'll continue here.
When we look up at the sun from Earth, it seems calm and unchanging. The truth is quite different. In addition to these abrupt changes in activity, the sun also has a long-term, more regular pattern of change. This pattern is called the sunspot cycle, and a single cycle lasts for about 11 years, although it can be as short as 8 or as long as 14, and it can vary dramatically in intensity. During one cycle, the number of sunspots, a good indicator of solar activity, goes from low to high and back down to low. Solar minimum represents a period of time when sunspot numbers are relatively low, and solar maximum represents a period when sunspot numbers are relatively high. During this cycle, the location of the sunspots also changes. They are at middle latitudes during solar maximum and move closer to the equator as the sun approaches solar minimum. At solar minimum, there are sometimes no sunspots to observe. At solar maximum, there can be many at the same time. The number of sunspots is important because sunspots are the visual markers of where powerful magnetic fields have emerged from the sun's interior. These magnetic fields power solar flares and coronal mass ejections, which can affect Earth and other objects in the solar system. As the sunspots increase, so does the frequency and severity of flares and CMEs. The sun's 11-year cycle is a symptom of a longer 22-year cycle called the solar cycle, or Hale cycle, which affects the sun's magnetic fields. Every 11 years, the sun's poles flip. North becomes south and south becomes north. So every 22 years, the poles return to the position where they started the cycle. The flip is due to the complex movement of magnetic fields inside the sun that are constantly stretching, twisting, and crossing as solar material bubbles up from the sun's core, but the exact pattern of movements is not yet mapped out. Because the sunspot cycle follows a similar pattern regardless of the orientation of the poles, it only takes half as long as the solar cycle. The two cycles are different, but the 11-year sunspot cycle is often referred to as the solar cycle, which can be a little confusing. Right now, the sun is approaching solar maximum, so flares and CMEs are more common than they were a few years ago. This cycle may peak in 2013 or early 2014, and should reach its minimum around 2020, although predictions about the sun are still uncertain. The slower than expected progress of this sunspot cycle has led some to speculate that the next sunspot cycle might be very minimal, with few sunspots even at solar maximum.
And that's literally what I'm reading right now. Just gonna pause it for a second and show you this graph. Oh, I gotta get out of here. Okay, so I was just looking, and this is the graph that they were talking about. It's the same thing. So I don't know if you can see that, but there we go. So this was the last sunspot cycle. That's sunspot cycle number 24 that peaked in about 2014. That's what she was just saying. And then we had solar minimum in around 2020. So this is sunspot cycle number 25, and it's much less severe. Maybe that's clear, yeah. So that's a sunspot cycle. So what she was just saying was, because it's an older video, that they were predicting a very minimal sunspot cycle that it was going to peak around 2025, I think. So we're kind of on the upswing right here. But they're just saying in the article that it's very weak. That's what the sunspot cycle is weak. Okay. Go back to this. So I just wanted to share because I was like, what she said in the video was like literally what I was just reading on the internet. Okay. So the sunspot cycle begins when the number of sunspots is very low, but we start to see an increase. And you may not see sunspots for quite a while, but you start to gradually see them increasing in number. Again, when we have the bottom of the sunspot cycle where the activity is very, very little, that's when if you see sunspots, they will appear at the equator. But as you start to get into the peak of the sunspot cycle, that's when the sunspots kind of move halfway between the equator and the poles. And that's, like I said, that's because if you think about, you've got like this strip in the middle of the sun, which spins faster. At the edges of where the speed changes, that's where you would see the most activity, because that's where you have stronger magnetic lines, because that's like kind of the boundary between the slower rotating gases and the faster rotating gases. So here you see in the bottom right corner, the difference between solar minimum, where you see almost nothing or you see nothing, and solar maximum. And you can see these two lines here and here. So this is what I mean. If you've got this gas is moving faster than this gas, then at the border, you would see more sunspots because the magnetic fields are stronger there. Okay, so it's just like this increasing and decreasing number of sunspots is how we keep track of the cycle. All right, so now we get into what do we call the different activities that occur during the sunspot cycle. The first one is called a prominence. And so it's a great cloud of glowing gases. It just kind of arches above the surface. Then it will eventually fall back down. Nothing actually gets released from the sun in a prominence. But here you can see the approximate size of Earth compared to the size of the prominence. Again, we are following, okay. That just decided to freeze. Okay. We're following the lines of magnetism. And so you can imagine that the magnetic line goes from here to here. And so you're going to have a sunspot here and you're going to have a sunspot there. So I'll just draw it in black. So there's a sunspot here, sunspot there. And you're going to have a magnetic field going from one sunspot to the other. Now, the thing is, sunspots also rotate. So they rotate in this direction, as well as spinning with the rotation of the sun. So as it rotates and as it spins, you can imagine that these magnetic lines sometimes get twisted, and that's when you might have a solar flare or a coronal mass ejection. A prominence is just a huge arch of gas that kind of explodes out from the surface and then eventually falls. Again, they follow a curved magnetic field from one sunspot to another. Prominences can last for weeks up to a year. That's taking a long time. So we're just going to go. So you can see how it's actually that it looks really pretty, to be honest, even though it's like several thousand degrees gases. But you can see that most of it's falling back down, almost like it's raining superheated gas. Just as a reminder, what you're looking at here is the photosphere. You see how it looks really grainy from the boiling gases that are coming up from underneath, and then the chromosphere is this reddish glow here. Okay, does it get any better than that, or is that it? But you can see how it continues for a long time. Yeah, I guess that was it. And then finally kind of starts to get a bit weaker. All right. All right, so a solar flare is the next thing. That is a sudden outward eruption of electrically charged atomic particles like this. So prominence is much more, I guess, gentle, where you have this kind of gradual rise of gases that follows the magnetic field, and then eventually it falls back down. A solar flare is an eruption. Again, it increases the strength of solar wind.
How big in size are solar flares?
So that's
this
a solar
impressive
flare.
NASA video taken on February 20.
You can see already the difference between a prominence and a flare, because the flare, it's just spewing gasward outward and not having that arch, that typical arch of a prominence. Let me rewind it.
How big in size are solar flares? This impressive NASA video taken on February 24, 2011 caught the public's imagination when news and media outlets described this flare as massive or huge. To fully appreciate its size, though, we need some perspective. So let's use something we're a bit more familiar with, the Earth here for size reference. The Earth has an average diameter of 12,742 kilometers, with average outstretched arm lengths of 1.7 meters, 7.5 to 8 million people holding hands would measure the thickness of the Earth. Next to the Sun, the Earth is but a pebble in space because the Sun's diameter is approximately 110 times that of Earth's, enough to fit approximately 1 million inside. Keeping proper ratios, let's now zoom in and fly this model Earth to a position relative to the flare in the video and do an approximate size comparison. Now we begin to see and understand the true enormity of solar flares, and also understand better why they can affect us when these eruptions coincide with our planet. Streams of highly energetic particles emitted from larger flares can be hazardous to unprotected astronauts and cosmonauts, and problematic for electrical and radio systems. With this Earth versus flare size reference, we can also do a quick estimation of the final length of the flare by stacking one Earth next to another as the flare unfurls. What we end up with is a flare length that is approximately 30 Earths stacked end to end. So after watching this video, the next time we hear that a solar flare is massive or huge, we can know that it's likely to be equivalent size to dozens of Earths. If you've enjoyed this video and found it informative, please share.
All right, so that's solar flare. Wait. You can see the bottom right corner.
Solar flares may seem like faraway events, but they can damage satellites and even ground-based technologies and power grids. Every 11 years, as the sun reaches its maximum activity, they become bigger and more common, and that increases the chances that one will significantly affect Earth. So what are these solar eruptions? A solar flare is basically an explosion on the surface of the sun, ranging from minutes to hours in length. Large flares can release enough energy to power the entire United States for 1 million years. Flares happen when the powerful magnetic fields in and around the sun reconnect. They're usually associated with active regions, often seen as sunspots, where the magnetic fields are strongest. Flares are classified according to their strength. The smallest ones are B class, followed by C, M, and X, the largest. Similar to the Richter scale for earthquakes, each letter represents a 10-fold increase in energy output. So an X is 10 times an M and 100 times a C. Within each letter class, there is a finer scale from 1 to 9. C-class flares are too weak to noticeably affect Earth. M-class flares can cause brief radio blackouts at the poles and minor radiation storms that might endanger astronauts. It's the X-class flares that are the real juggernauts. Although X is the last letter, there are flares more than 10 times the power of an X1, so X-class flares can go higher than 9. The most powerful flare on record was in 2003 during the last solar maximum. It was so powerful that it overloaded the sensors measuring it. They cut out at X17, and the flare was later estimated to be about X45. A powerful X-class flare like that can create long-lasting radiation storms, which can harm satellites, and even give airline passengers flying near the poles small radiation doses. X-flares also have the potential to create global transmission problems and worldwide blackouts. The seriousness of an X-class flare pointed at Earth is why NASA and NOAA constantly monitor the sun. NASA's heliophysics fleet of spacecraft can now see the sun from every side and in many different wavelengths. This unprecedented coverage is enabling scientists to predict and detect space weather events like flares and CMEs with ever greater accuracy. With advance warning, governments and companies can take steps to protect their technological infrastructure so that the worst scenarios will never happen.
Okay, so in that video, they were explaining that solar flares are classified based on strength, and that's why it's important that you have organizations like NASA and other ones in other countries that I don't know the name of because I'm not from there, watching the sun during the sunspot cycle, especially when we have astronauts on the International Space Station, because exposure to increased solar winds is dangerous. So this was in 2011, at the beginning of the last sunspot cycle. There, you saw the flare there, boom. But you can see that most of the material sinks back down. Now, a lot of times, this is actually a coronal mass ejection, what you're seeing right now. Ugh, okay. Oops. A lot of times you'll see, there we go, that they actually block out the body of the sun so that you can see coronal mass ejections and flares more clearly. So these are all flares, but that one at the end is a coronal mass ejection, which I think is the next one. Okay, that's a flare. Okay, so when you have a strong flare, sometimes you can have particles that actually escape into space. And that, like I said, increases the strength of solar wind. And sometimes they can cause what's called a magnetic storm on Earth if they come into contact with our magnetic field. And that interferes with our communications because we rely so much on satellite, not only for our cell phones and our TVs. So imagine just if we had like a complete blackout and your cell phone didn't work because, you know, you communicate through satellite being bounced around, and you can't get TV or radio. So the government literally cannot tell the people what's happening, and ATMs don't work because they communicate with satellites with their banking network. So that would be really, really bad. Okay, before I get to CMEs, I want to talk about the nice side of magnetic storms are auroras. So when the ionized wind, solar wind, come into contact with our magnetic field, so again, we've got Earth, there's our poles, our magnetic field is like that. Okay, it's bad drawing today, whatever, you get it. When it comes into contact with our magnetic field, it is just like how the prominences follow the magnetic fields on the sun. It's going to be directed to the north and south poles. Okay, and then you get something like this because they ionize the gases in the atmosphere. You also get this, so you can see how the gases circulate through the atmosphere. It's a pretty rare one to see really pink colors. Generally, you see green and blue for oxygen and nitrogen. I don't know, I thought pink is hydrogen, yeah. It can also tell you how far down in the atmosphere the gases are ionizing because hydrogen is in is it called? The stratosphere, the highest level of our atmosphere. I don't remember anymore. This I thought was really cool. This is a picture of auroras from the International Space Station. I'm not sure which continent this is, but obviously you can see like big cities because they're really bright lights. So you can see the layer of aurora here. And this is one of the solar panel wings of the International Space Station you see right there. But that was a really cool picture. Oh, yeah, there's another one. So part of the International Space Station up here. And then this is solar panel. So Scotland's pretty far south to be seeing northern lights. So this is in time lapse again. So it's been recorded and sped up a little bit. Green is a very common color because green is nitrogen. And our atmosphere obviously is mostly nitrogen. Again, there's that pink from the hydrogen. And sometimes you'll see a bit of blue from the oxygen. Okay, I think you get the picture anyway. So it was in northern Scotland, they said. And you can see how the pink is in upper layers compared to the green. That's where the hydrogen is in the upper atmosphere. Anyway, pretty. Okay, so you see it in your poles. But it also occurs at the South Pole, but we don't really have continents except for Australia. They're really close to the South Pole. So they'll be called either the Northern Lights or the Southern Lights. I do believe Aurora Borealis, Aurora's lights, and Borealis is northern, and I don't know Latin for southern. These are happening many kilometers above the Earth's surface. And of course, they occur most frequently at the peak in the sunspot cycle. So about 5 times a year during the peak of a cycle. The last activity is the most violent. It's called a coronal mass ejection. And based on the name, coronal means it's from the corona, the outer part of the atmosphere. And mass ejection, this is when you're going to have tons of gas, like literally tons of gas that are ejected and flung out from the sun. So this occurs because of the shift in the sun's magnetic field, and it can release billions of kilograms of gaseous ions at up to 2,000 kilometers per second. They create radiation hazards, especially to satellites. So these are the kind of ejections, these are the kind of activity that can fry our satellites if we don't see them coming. So again, here, they've outlined, this is the outline of the sun, but they've blocked out this bigger area so that you can actually see the coronal mass ejection. Remember, you cannot see the corona except during a solar eclipse, but what they can do is they can cover up the sun so that you're allowed to see it. This is billions of kilograms of gas that is being flung out into space. That wasn't it. That was it. I think. Whoa. That down here. down. Holy crap. I won't play this whole thing because it's just a bunch of coronal mass ejections one after another. But again, you can only see it if you cover up the body of the sun so that you can see the corona. And you see the timestamp down here. So these are occurring at different dates and time during 2012. Here's, oops, that was the next day. Here's 2012 as well on the 19th. You can see how swirly it looks because of the magnetic field. Okay, I think this is all taken around the same time, the 19th of January, 2012. Yeah, it's also the 19th. Okay.